Hey, what's happening, everyone? How are we doing today? We got Kayla, Trace, Ben, and Cliff here. How you doing? It says, Brian, when I'm adding in test and hold on my app, am I doing the test and the holdout on the converted time series data or the raw data? Please take I'll take a look. Let's see what that's awesome. I'm excited. There's so many great things. Ben, I would take the holdout first, and then, especially if you're making predictions, you want to untransform them. Would it really matter? Like, you generally want to look at how you're doing untransforming stuff because you want to make predictions that are untransformed. So you can do the transformations and then you can bring things back by untransforming them. So yeah, let me take a look over here. I should have. Okay, let's see here. Oh wait, latest update. Oh my gosh. Oh my gosh. Oh, I ran the wrong thing. Oh my gosh. Holy mackerel. Simple models, complex models. Choose the file. This is absolutely, oh my gosh. Vector to convert. Oh, so does it so I don't know if you can, oh my gosh, this is insane, Kayla. ARIMA model, naive model, mean model, drift model. Oh, I think I just broke it. Oh my gosh, this is absolutely insane. Can you talk about 3D? Yeah, let's do it here in a second. You got it, Trace. I'm confused on those two. Teach me your ways. So definitely meeting with people, asking people questions. This is absolutely insane, Kayla. Looks like I had a replacement error, but this is absolutely amazing what you have going on right here. Just I like debate showing people other, I don't know. I debate it, but oh my gosh, wait, interpretation of Armis. You wait, where'd you grab these? Input vector, and I say the model's plots headers into reactive values. Yeah, this is absolutely astounding right here. Just the this is just like just the way in which you've taken this to like next level. Like once again, what you're doing here, I think, is and you're adding in the complex models here. Oh, is it okay? Wait, does the complex models tab work right now, or is the complex model? I did a lot of research and yeah, Kayla's been going, and I want to say is thank you for going above and beyond because what you have right here looks amazing. It just should I show it for inspiration? What do people think? Should I show it for like inspiration? Kayla, it's your call. Just it's absolutely astounding. So yeah, I clicked the complex tab and I saw that, and we're here in 1980, and yeah, wow, it's just placeholder tab. Yeah, I clicked it and it didn't do anything. I was like, what's going on? Placeholder tab not doing anything. So definitely hugely above and beyond right here with the type of plot, the drop down menu, the frequency. Do people want to see? Or we'll do it. Just a little inspiration right here to see what's this is astounding. I'll show you. Take a look. So Kayla gives permission, so let's show it. And once again, this is completely, I think, above and beyond. We've got here the data tab. It's got the search feature. We got here the simple models right here with just different types of models right here, like the naive model switching between the drift model right here, all these different things. I had a small problem with the seasonality. I think it's crashing it. The ARIMA right here, this is, if you just want to go crazy, when you select the ARIMA model right here, if you were to have it, it looks to be doing the 0000 ARIMA right now. Yep, so she made a dashboard right here, like a full-on, like, this is just the time vector right there, the time order vector. But loading in the data file right here and then selecting the frequency of the data, switching over the frequencies, mainly just changing over the plot right there. And we'll throw in some seasonality stuff. But you got your prediction window right here. I don't think anyone ever predict more than 20, so that's a good amount. Like that's a good. I like that this is with a slider right here. So really good right there. Click on the naive, check out the residuals. Yeah, let's go do that real quick. So the naive right here, boom. Let's check the residuals. Wow, just like, oh, I love the tab. I love the inner colors on this and everything. Oh yeah, so you can automatically see what's going on right here. If you add in, I'd put maybe a transformation checkbox here so you could do the Box Cox transformation on the data. Does that make sense, Kayla? Like I'm just throwing Kayla some suggestions right here. Like I'd maybe throw in like a Box Cox, like if you put a checkbox or something like Box Cox transformation, or you could have different transformations, just depending on like what you want to do. But It updates for, yeah, I know, right? So that's what happens right here. So we go over here and we just go to like the mean model, and then you go over to here to your check residuals, and now you can see we got different residuals right here. So just updating with each one right here so we can see what's up, anxiety? Good to see you here. And if you check the accuracy of the model right here, even in interpretation right here, the RMC describes typical miss of the time series. The lower the RMC, the more accurate the model when analyzing data in two separate sets, training and holdout tests at lower difference. And so, yeah, getting ready for some training and holdout right here. And we can see the RMSE value right here. You can use some printf right here to reactively grab text. We could talk some about that at a later time. But this right here is... once again, I think this is absolutely amazing. I don't think that, okay, good. Wow, look at that. Just the seasonal naive does not that bad of a job on it. Let's check the residuals of the seasonal naive. We're still missing a lot of the autocorrelation over here. And we still have some sort of differencing maybe that we could take out of the model. So maybe you could put a button to do differencing, but the ARIMA could handle that too. Am I giving you some ideas here, Kayla? Like, really, you're just in the fine tuning of this. And this is now just adding in, maybe you could put ARIMA on its own tab if you want. Like your check residuals page, I'm wondering how that's going to connect since you've got two tabs here, like the complex models tab. But like this right here, I think is absolutely amazing. You can go right here and close that down if you just want to take a look at the main dashboard. But yeah, I think this is excellent right here. And I think the analysis page right here, the checking of the accuracy really does. And great job on these windows right here. Just super amazing job. I'm actually going to look at your code to see how specifically you made this right here. A lot of researching. Love the graphics. I mean, this looks like a professional grade item right here. I was thinking having more. Oh yeah. Just, I mean, don't spend the amount of time needed. But yeah, so don't go too crazy. I mean, like, no, like this is I'm super impressed with. And so if you can see where we're trying to get things to, if you have problems connecting your buttons, and Kayla, what advice do you have for people as you've been building this out, as you've been growing with what we've been creating and doing, as you've been growing this, how did you do all these models right here? Which really is a lot of copy pasting after a while. Like, I'm assuming, am I correct that all of this right here is basically copy pasting and then just adding another button there? No, I think this is great. I think it's excellent. And for those wondering how you build this, you build it one step at a time. You don't build the whole thing. You say, let me get the naive model working. Oh, some if else is right there. Yeah, because it's going to be if else with the buttons. So you say, let me get the naive model working. Let me get the mean model working. And then you say, if this is selected as the input, display this plot. Else, and probably just, you might not even need else. You could just do a bunch of ifs, right? You could say, if this is input, put this plot out. If this is input, if input equals this, plot this. If input equals this, plot this. So the last one could be an else, but I might just do if and check the input, plot this. If render plot this. Does that sound right? Store into render plot this, and then the render plot is the plotted object. Is that theoretically correct right there, Kayla, on what you did? Each if else contains the code for the model, the autoplot, and the header, and saves them as reactive values. Oh, wow. So yeah, each one's created as a reactive value. And then those reactive values are carried out further down here into your accuracy where you grab the accuracy. So this is a reactive model right here, which I think, you know, what's interesting, Kayla, I'm just thinking how far you've come with this in like a week or two. I was showing you how to do, and of course you were looking these things up too, but I think I don't know who I helped on what now anymore, but you're making me think a lot. And I really want to see how you made everything look so nice and flashy, because I understand all the theory you're talking about with your reactive models. And then you're doing, if a certain input is selected, then a certain reactive model is created. And then the auto plots are created based on that reactive model. So all your auto plots and stuff. Then I use the render with the reactive values, so they are constantly updating. Yeah. So some really great inspiration right here. If this helped inspire you to think about how yours could be when you're doing different things right here, where you have different selections, but really, really great layout, just a different layout than what we've been doing, but a lot of good options. Do you want a separate tab with the different data of the training data? What I'm envisioning is maybe a thing right here to say % in holdout. So what I would do I know, right? I think we're going to keep progressing what we do in these types of classes because Kayla's offering me some inspiration. And I've got some ideas on how to start people off better. And we're going to put more check marks in the way in time series, more check marks to be like, you have to do this, then you have to do this, you have to do this. Because I think I jumped people a little bit too quickly into the midterm. Even though we tried to put help along the way, I think it'd be better if the homework assignments were more oriented to getting your app going. Yeah, great job. And so what I would add in is maybe a transformation thing over here to transform the data, because this data could use a box Cox transformation. And I'd add in a holdout thing over here. Or you could just have a tab and you could say holdout. You could have a holdout in transformations, or you could have a holdout tab. I mean, really comes down to design aesthetics then. Yeah. So much time and research, yeah. And then it just comes down to your imagination. And I want to say that that's the great thing about this is why do we learn how to code? Is because we can learn these topics, but then if we learn how to code and we make something, we can make something like this. Like you could tell someone this is a product at this point, like, oh, you can buy our product that lets you analyze the different time series models. All you have to do is load in your time series here, make sure it's the vector in the data set, and then you can change it based on it. You could even I don't know, there might be a way to have it look at it, but if you look at this right here, we're changing it. It is monthly data right here, starting in technically I think 1960. I think, did Kayla we work on this where it's grabbing the date? I helped someone with the reactive objects. Well, I think I know who it was now. But this is a drift model right here, just going through, drifting from the first point to the last point. So the linear model right here, if you look at how the drift model works, remember we should understand these theories right here. The drift model is a review of time series now. The drift I can't draw today. But know how the drift model works. The drift model is going to do this. Does that make sense? You did the day for me, yeah. We'll figure out why it's doing that. We'll have to, you know what I should show everybody? I got to turn on the options to do this though. 2 seconds. Let me see if I can get this going. I will show something that'll blow people's minds here if I have it on. Okay. I'm going to show you something that'll blow your minds, and then we're going to do some 475 here. So please ask questions. Kayla, Kayla, you've taught me a whole bunch. I just want to put that out there 100%. How many questions have you asked me, Kayla, about like how to get things running or blah, 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 like anything? Just like, hey, Brian, this is not working. Hey, this is not working. How do we do this? Where should I look for this? How many questions have you asked? And at this point, I have been learning things from the questions you ask. So how many questions have you asked? And this is the only way to get things done like this. How many questions would you say you've asked? Okay, I was thinking that over here. I'll show you something that'll just be absolutely insane. I think we're approaching infinity. The only way to do these things is to ask so many questions, to keep asking. So something I've put on here that I can help people put on is like a debug. I'd have to show you the steps for this, but watch this. Everything I just clicked in Kayla's app can be visualized here, going through the steps. You could zoom in and see what's going on right here. It's a little bit much going on. Smaller apps are easy to look at, don't worry. But you could literally hit play and watch my inputs as I go through here and go through and run things in Kayla's apps. But this is showing, like, if we look over here, what's happening right here on this whole thing. This is the output of the plot right here, creating from all these different things, whether we're putting in certain inputs. So it's running all this right here. We could zoom back out, but this is showing what is happening in the app in real time. It's a bit much, can get very, very complicated very, very quickly, but it's a visualization of all the code running, and then you could see what's stored in at certain times. Like you could see currently what the brain of the app is holding, and it's just a whole spider web, which yours is very complicated, and I clicked a whole bunch of buttons. So it's just everything that ran through as I clicked buttons in your app and what it was doing at that time. So you could literally go and be like, at this current time, what is stored into here? And this is the time series data right here, and what is being carried through right here. That's the white noise fit right there in your model. Yeah. And so pretty good stuff right here. You can just watch as I'm changing values, and the values are changing throughout your app. But if anyone wants to do this, is a little more advanced. I've been using it to debug people's issues and hopefully get a better idea of what's passing through. Yeah, let me hop to Space and send you the guy's thing on this. I'm trying to remember what it's called again. Let me go to Space. It's a really good way of like looking and debugging stuff. So let me put that in the chat, and then we're gonna do some 475. So it's all about practice. It's all about practice. What is it? It's called Shiny React Log. Okay. I'll send you the video I watched on it. It's pretty new. Debugging the state of Shiny. React Log 2.0. Here it is right here. There's Shiny React Log. They walk through the steps on how to get it. You gotta use DevTools. Actually, I think you just do library or install.packages React Log. They had it as a dev tool install, so I think you can just do it normally. And then you have to hit, like, he uses a Mac, so he says Command F3. I wish he said on a PC Control F3, but I was able to figure that out. It didn't have instructions on doing it, but it stores like a whole reaction log of what's going on, and then you can see what's going on. I've been trying so hard in Shiny, it just hasn't clicked. It's one of those things that it's, you know, like one day it just clicks, but Ben, keep sending me your work and be like, hey Brian, it doesn't work, this is broken. We're gonna look at some 474. But it's just practice. I that's the hardest thing, right? It's like, hey Brian, this won't work, I can't get this object to work. Start early. So remember, we are having that update to your grade. So if you did poorly on, I'm getting the assignment 474. If you did poorly on the midterm in 475, then please, please, please say, hey Brian, can you take a look? This is currently stuck. I'll try to update and help and figure it out with you. We'll work together on it. Well, with that, it is time to hop back into some 474. They can't for Shiny really help. Yeah. And Kayla, you said once again, you don't think we should make that mandatory, right? I'm going by Kayla's advice right here. Kayla, I'd consider making him like part of the first grade. Also, at first I coded a lot of things outside Shiny and then moved into the app. Yeah, that's the thing too. Like functions, like don't code the function at first. Get it to work on a data set or something outside of it. You know, get your accuracy working, get your forecast working, get these things working, and then think about how it goes into an app. Like get it working outside of it first. Yeah. And then Ben, you send me a Ben. Just send me a, hey Brian, this won't work. Page can't display this. And there's been a few issues. I'd say I can solve about 90% of stuff. A few people have thrown me things, and I'm like, we're gonna have to come back to this because I'm just stuck on it. A few people have stumped me, and I'm like, no, I hate getting stumped. I've run into errors like xvar not found. Yeah, Ben, send me it. Send me it right today, and I'll take a look. I'll be getting the messages here in a little bit. I got a meeting right at the end of office hours, so let's hop into 3D. Starting out here on 474. Let's do some 3D. Here we go. If you don't know anything Snow what dplyr does, you don't understand what's going on. Yeah, oh, the dplyr stuff at the end. Whew, 3D, 474, yeah. I think I got pretty far into dplyr. I think I did some of that data camp, and then at the very end, it's like, oh yeah, because you're saying the shiny stuff with dplyr. Maybe I should teach people dplyr. So we're looking at an ideal elbow plot right here. Okay, so what's our saying? What we got here? So what am I making right here? What kind of elbow is that? Who knows? 3-letter word. Wow. Chair's just creaking away. Bad elbow. That's a bad elbow. So I don't want to quite give this one away. I don't want to give away, but when we look at an elbow plot, we want to see good elbows. Good elbows. So what we really want is we got here bad elbow, good elbow, and then impossible elbow. Impossible elbow means the within cluster sums of squares would go back up in some way. Just, it can't happen. We're looking at the within cluster sums of squares for any of these. And this is as we increase k, which is the number of clusters. So increasing k, the number of clusters, it literally has to decrease the amount of, it has to decrease the amount of sums of squares, the within cluster sums of squares, which is the error. What do we mean by error? Well, we mean if we have a cluster center here, a centroid, then we have points. Well, when we look at the error, we have a distance it is away. Let me do that in a different color. We have a distance the point is away, and then we square that distance to get a squared distance. And we would do this for every point. Like we'd look at the distance. This one is away right here. There's its distance, and then we square that distance. Now, we can do these distances in different ways, but let's just do it with Euclidean methods right here, which is going to be the shortest distance. So when we look at this within cluster sums of squares, if you add more centroids, which are cluster centers, the Ks, then we would see smaller within cluster sums of squares. Like we have a whole bunch of points right here. Then we might have 2 cluster centers, and then we would have the error these points have from their cluster centers, or we could have 3 cluster centers, 4 cluster centers, 5, 6, 7. And now if you notice, this point right here that was assigned to this centroid is going to get assigned to this centroid, or maybe that one. It's very close to both those. But why would we want to stop increasing cluster centers right here? Why would we not want to be like, well, let's just put as many cluster centers as we want? Because eventually, and we'll reach the impossible one, eventually, as we increase the sums of squares, as we increase the clusters, brain jumped a moment there. As we increase the clusters, the sums of squares within the clusters will do what? As we increase the clusters, this is where we talk about everyone's house as a gas station. Like if we make everyone's house a gas station, everyone lives at a gas station. So no one has any distance from a gas station. Achieved the goal. It's not the goal. It's not the goal. The goal is to find out the right amount of clustering where we might see some sort of natural pattern in the data. It might be visually apparent, but at this point, this one has a very visual apparent pattern, and I should probably redraw this. It would do something like this right here. It'd go. So if we were to look at the pattern I made in the data, the answer to the question, can't really do a 0. You can't have things in 0 clusters. There is no 0 on this axis. The answer to this question is going to be what right here? Which I've drawn more on it. I'll start to make it look more like the answer it should be. The answer that's apparent I think you're getting it, Trace. See, I'm like, Trace is getting it right here. Trace is knowing what's going on. So it should be, in Murray, you can't make impossible elbows. You can't make that impossible elbow. If you know what I'm talking about, you can't make impossible elbows. You want the good elbow on the answer. Does that make sense? I think Trace is getting it. I think Trace knows exactly what to do for this to get a good elbow on the answer. Because now the elbow is on the answer of 2. And you don't always get things this awesome. Remember, the elbow can't go back up. Generally, it will kind of keep going downward a little bit. You should be getting some sort of decrease in within cluster sums of squares. Does that make sense? You will generally get some decrease in the within cluster sums of squares as you increase the number of cluster centers, unless points are 100% on top of each other. Yeah. I mean, at the end, you might have points on top of each other, but yeah, especially at this point, we'll see some decrease. It might be very small decimal differences at times, at least in this example, but increasing the number of clusters, unless points are on top of each other, unless you've gotten it to 0, then you will see a decrease in the within cluster sum of squares. Is this making perfect sense here, Trace? Like, this really directly answers the question. If you understand the theory behind it at this point, you should be like, I know what I'm entering in for those numbers. How you doing, Trace? Think you got how to make that good elbow plot to achieve? Because in this question, it says we are trying. So we want to see the ideal elbow plot. We want to see, look at the elbow plot above to see the clustering scheme exists due to natural selection in the data. In business analytics, we rarely ever naturally separate into distinct groups. In this case, is no exception. In the ideal within cluster sum squares, this is the ideal vector. Replace the 5 NAs, NA, missing this right there, with actual numbers. When ideal within cluster sum squares is plotted for K, the natural structure in the data would suggest 5 clusters. So we want it to suggest 5 clusters. 1, 2, 3, 4, 5. So you have to think about how would this naturally suggest 5 clusters. Does that make sense? And then you're going to run right here. So plot the elbow plot right here. And so right now, how's the elbow plot look? Don't do this. Maybe I'll show you a not ideal. Right now, it shouldn't look that ideal. Let's talk about a not ideal one. I'm looking at the differences right now. Why is this not... That's not good. 1, 2, 3, 4. I'm afraid someone's going to put this, but don't put this answer. It's not ideal. Why is this elbow plot not ideal? Ooh. Ideal means good elbow. Why is this elbow plot not ideal? You say, well, isn't that the elbow? No clear selection point. It's not our good elbow plot. Nope. No good elbow. That's good elbow, bad elbow. Bad elbow, good elbow. Bad elbow, good elbow. Here's the elbow. Remember Nessie from class? And then Loch Ness Monster. Why is this an impossible elbow plot? Why is that an impossible elbow plot? I think you're both seeing it. Why is that? So be careful. Hope my grader is... I would take out points immediately for this. I'd be like, yee, can't happen. Theoretically impossible. Can't do that value. That is white. I thought it was getting green screened. So, why can that not happen? And then we'll do the next question here. Why is that impossible? So the answer for why that point behind my head is impossible is because, as we were saying, as you increase the number of clusters, and these are the centroids by which the data can be close to, increasing the number of clusters will always make points closer to cluster centers because you're adding more gas stations to your town, and these are the residents, for our analogy, and now people are closer. There'll be less error within the cluster for how far they are away from cluster centers. So you are decreasing at all times, but at least this data has a natural structure of 2. And you can see that right here, the natural structure of 2 with cluster 1 and cluster 2. It's very, very apparent for this data. And it's easier to talk about examples that are like examples that we can see the answer to. And it's like, oh, that data has a structure of 2 clusters, and the elbow plot indicates this. So we would be like, let's go for 2 clusters. If 2 works good, we could look at 3. I wouldn't go for 3, though. Okay, I'll look at it, but it's probably not going to be great. But there are no right answers, right? Unsupervised learning. There's no real answer to the question. It's like, well, how good does the answer work? Well, that's got that question. I think people are good on this question. That's an impossible elbow plot because the sums of squared error cannot go back up. The within cluster sums of squares cannot go back up as we add clusters. Back to the main screen. Awesome stuff. Let's do another 474 question. Let's not give it away completely, but let's go and do another 474. Here we go. Since there's no natural choice for the number of clusters, let's choose K5, but K means on the data 6 homework scaled. So it looks like I need to scale the data with centers 5 and inner max 30 and end start 25. Left arrow the results into K means. Okay. Let's go take a look at this right here, and let's not do the exact same thing. Let's go look at some survey 10. Look at some survey 9, I think. Let's go do this. Here we go. So imagine, we work for a gym. Let's go pretend we work for a gym right here. We got some gym customers. Okay, there's data survey 9. And let's go to names, survey 9. Okay. Do you use chopsticks? I totally forgot that question was in here. What's that question all about? Wait, where's my data sets? Oh, I'm in the forecast package. Data survey 9. What's the answer to chopsticks? It's just no and yes. Do you know how to use chopsticks? I think was the question. What would be related to gym? H1N1, flashbacks, current world near. Desired weight. We use survey 10 so much. I want to use a different data set. We got desired weight and weight. How much do you study? How much do you drink? There we go. Okay, let's go grab... I wish I could highlight it there. Let's go grab number of drinks per party. How much do you drink at a party? Periods in the way. Okay. We're going to do a clustering scheme based on this data. Let's call this data... New data. Let's go here to survey 9, and let's go to the column space on it. Concatenate a vector, rows, columns, we're good. And there's our first one we're taking. And here's our second one. We'll take somebody's weight. So all I'm doing is I'm selecting certain columns right here at this point. Desired weight. Does anyone see anything else major? We're gonna scale these here in a second. Scholarship. Is that scholarship amount? No, it's levels. You can look over there. It's a factor. I'll look over the screen. When do you want to get married? Kids by. What's up, Cliff? Good to see you here. Are you a business major? How much do you text? Hours work out. Oh my gosh. Perfect. Perfect. We're working for a gym right here. So that's exactly what we want to know. Last 2 digits of phone number. How attractive do you think you are? Why not? Why not? Okay. So we're making our own data set right here. And how much do you work? That sounds good. Hours of work per week. Okay. So we're going to have some issues with this. I should have grabbed Scholar. Oh, it's not amount though. Okay. New data. Okay. 24 warnings. Was that related to graphics? Yeah, it was. Okay. Stupid. Go away. Graphic error. And so now let's go to new data. And I want you to think about this. If I do a summary on the new data, what is the issue with the new data? And this is a great review right here. What do you automatically see as an issue for the new data? Trying to get it all on one screen. So what do you see, especially with attractiveness, and someone works 168 hours out a week? I'm going to start removing them while you think about maybe they also work that many hours per week. Which person is the max right there? We're removing that person. Which dot max? It's not standardized exact answer. Like, we don't have z-scores right now, so the scale of things like weight are going to cause problems. Survey 9, $, workout. Someone was being funny. Haha. Person number 5. So person number 5, you gone. Was it another person trying to be funny too? We'll find out. Someone says they work. Oh my gosh. Some data validation right here. I'm going to move another person. Number 4. So concatenate minus concatenate, right? I always get a little iffy on this one. Okay. Okay, now we're doing better. Okay, I'll take this. Okay, do you reasonably believe someone could work out 60 hours a week? I don't think most people are doing that, but that would be brains breaking. 8 and the decimals 8.58 hours a day. I mean, I'm not saying most people would do that, but if someone told me they work out 8 hours a day, maybe they're a professional athlete, like they could be our star quarterback or something at UT, saying I work out 8 hours a day, like they've got like a 3 hour in the morning, 2 hour midday, 3 hour in the evening. Like, I mean, if your job is to be an athlete, you're working out 60 hours a week. Maybe they're a cross country runner and they're running long races and stuff, and they're going out running on 2-mile runs a day, and then I don't know. I don't know if that person, the person who said 168 was messing with us. So, yeah, hours work per week, 70, totally reasonable to believe. 60 workout hours. Imagine if you just worked out as much as you worked a job. Yeah, it'd be pretty interesting. And so Trace and Cliff are pointing out we need to standardize this because, or Trace is pointing out it's not standardized, it's not z-scores. So now that we have our new data fixed, we don't really got to worry about, we found our maxes, we removed them. Let's go, because I just don't think, I'm removing those people not because they're outliers, I'm removing them because I just don't think someone works out 168 hours a week. That is literally the amount of hours in the week. If you don't believe me, 7 times 24, 168 hours in the week. So they don't sleep, they don't eat, all they do is work out. I don't think that's true. So I think they also said they were a job person too, because if you look, we removed them. So someone was answering, trying to be funny. Haha. Maybe their job is to work out. All they do is work out, and they sleep and work out. I don't know. I don't trust them. Let's go right here. And you know what? L apply, I think, will be our best friend right here. we're going to take the new data and we're going to run the scale function. Will it work like that? No, it doesn't work like that. Oh, really? Look at that. And it's putting out in a list. I think it worked properly. Let me look at the output of this again. I think it's doing every vector and it's running out of space. So let me go to unlist. Oh, we'll do sapply. Yes. So if you're wondering what sapply is smart apply. So what smart apply does is it looks at the object you give it and then tries to figure out, so how did sapply work right here? Sapply saw that I gave it a what? Sapply, so what did sapply see that I gave it? What did sapply see that I gave it? When the question says K5, is that talking about the number of centers? Yep. So if you notice right here, it saw that I gave it a data frame, and it's returning to me a data frame back. So let's go here to scaled new data, new date, and let's store it into here. Here's our scaled new data, and so we're good on this. I hope that missing this doesn't cause an issue. Might need to do complete cases on this one. We'll find out the hard way. So right here, we've got our data scaled. We might have to do some transformations, so follow through your example right here, carrying down your data. But this is the data I'm going to use right here. I won't worry about if it's... Do we do transformation? I think we transform this data. No, we're good. We can transform it. Okay. And let's take a look. We're here towards the end of this one. My data is now scaled, so nothing's going to have undue influence. Print to the screen, the centers. Oh, we haven't done our clustering scheme yet. Let's choose K5, K-means. Okay. And let's go to K-means. There we go, K-means with stats. And here we are. Let's go ahead and run our data, iter max, and start. Good to go. And then there's the algorithms people use on it. McQueen? Trace is so you can see the output or not. See the output sapply does an unlisted data frame and does the sapply, smart apply, looks at the object you give it, and then it returns back. You have a scale it earlier on. Yep, exactly. I was just doing the quickest way to scale data. I was like, oh, let's just do an sapply right here. Let's just apply the scale function to all the vectors. No transformation is done. That's what I was thinking. On the coming up data sets, we will be transforming them to achieve more of a normal structure. So one could argue maybe transform it. I'm not the biggest transform person, but you need normality sometimes. So centers equals 5. And do we have an iter max? Iter max and end start. Iter max, which is the amount of times we'll go till we try to reach convergence. And end start, 30 and 25, I'm reversing it. And then end start is going to be always let it autocomplete. It's easy to make typos. There we go. What's it saying? Oh, it's mad about the NAs, which I said it would be. Your data won't have NAs. Mine does. Complete underscore and no. Yours doesn't have to do this whole process. Complete cases of the rows of this. There we go. Should work now. There we go. There we go. Now we need to store the output. Does this make sense here, Trace? Let me show what the code I've ran is. I ran into the problem that my data had. It's showing me the full output of it. We'll worry about that in a moment. But it's showing me right here that my my data had NAs the first time I tried to run it, which I thought would be a bit of an issue, so it can't evaluate. So I removed out the people who didn't answer survey questions. So now I'm going to try to group this. Starting out the React log video says to use command F3, control F3. Control F3. Yeah, that got me too, Kayla. Control F3. Just hold control and hit F3 and then boop. And then it'll say make sure options shiny React is on. Like you have to do, it'll tell you, it'll say like make sure you run options shiny React equals true, which will then trace it. Then go in, click a whole bunch of buttons, and then you'll see the literal pace of what you're doing, and you can see what is stored. So if you're looking over what something specifically is doing and where it's storing and where it's being handled and if it's being passed through, like you go in and just do a few simple actions and then you run the React log. If you do like 50 actions, you'll see a whole sequence of what you did. So it's much easier to be like, how is it handling this object? Do a few things and then hit the React log and be like, oh, that's where it's handling it. Okay, it's stored into this currently, which you can kind of tell, but it's really helped me looking at other people's apps to because since I gotta like brief myself on their code and like go through and I'm like, okay, let me just visualize what's going on here. I ran the options and tried Control F3, but it yeah, might have to look at that. We have to like screen share or something. Yeah, it might be doing like it might actually just be doing function 3. Mine does it with Control F3. It's got to be something F3. Maybe your F keys might be off or something. Good question. It's got to be something F3. It's something Command. Yeah, Command F3 works for. And she's on a PC right there. So yeah. Trace helping out. Nice job, Trace, right there. Let's go sort of k-means. So k-means outputs a list right here. And so you can see right here, we get a list of 9 things. These are just like a folder. Just think about, yeah, I know. I had a hard time too, and I really disliked in his video, he didn't make it clear. And so I had to figure it out. And I was like, oh, Control F3. We can take a look, Kayla. It's really nice to have the visualization, especially for like the high level debugging of it to find problems. Lenovo, and yeah, you guys are awesome. 20 points right there, helping out. Wait, watch this. Full screen. Oops. Oh, no. I got to unfull screen. 100 points. I got to fix those keys. Okay. Okay. Here's our clusters, and we want to grab this. So what are, I can't spell. There we go. What are these clusters right here? And I should actually look at it. Toots. Oh, man. Let's go look at that. Yeah. What is going on with those clusters? Yeah. One, two, three, four, five. Wait, why is that? Oh, that's the within. Yeah, it's the total. Yeah. Shift F3. Great job, Trace. I know, it's weird, isn't it? Function Control F3. Oh, man. Craziness. There we go. Thank you both. Great job, Kayla. You kind of figured it out. You kind of like, I like it. Trace and everyone. Worth that 100 points. Hey, teamwork makes the dream work. So what are these values right here? You have to know what these values are that you're getting. What are these values right here? Hint, I'll show you it differently. You ready? Let me change this. All right, what are those values right there? Windows doing the most. What are these values right here? And to think about it visually, it's like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2. So what are those values I'm obtaining right here by running k-means cluster in the list? It's kind of based on the number of centroids. It's the centroid assignment. Like observation 409 is assigned to cluster 2. Does that make sense, Trace? Observation 409 is assigned to centroid 2. Observation 375 is assigned to centroid 1, like cluster 1, which will be closest to centroid 1. But you can also see right here the totes within sums of squares. This is why we do like a for loop on one of these to like look at, you know, which of these would be the best way to go. Because the totes within sums of squares is 2,229.407. So if you think about if you're rerunning this algorithm right here, let me make look a little bit nicer. What you really want to do when you look at this, and this goes to like other questions with k-means, if you're looking at the output of this, watch. We're going to take this right here and put it inside of a for loop, and we're going to go to for. This is another question, and we're going to go here I and vector 1 through 10, and let's change the centers here to I, and then let's take after the for loop runs this, and let's take the within sums of squares and store this within our tote within sums of squares and store it into position I. And this is like your other for loop. And I need to grab this, store a blank one. And then what am I finding right here? Running the algorithm right here, I ran it with the different cluster amounts. I ran it with 1 cluster center, 2 cluster centers, 3, 4, 5, 6, 7, 8, 9, and 10. Then I stored the output of the total within, did I get the right one? Yeah, the total within sums of squares. Not for each individual cluster, and I think we're on a 10 cluster scheme right now. Those are the clusters, and then this is the total within cluster sums of squares. And we could look at each cluster and find out the error each cluster has. So the total of these, if you were to sum these up, because that's what the total within cluster sums of squares is, the sum of all the clusters. Is this making sense here theoretically, Trace, when you look at this? Like, there's 10 clusters right now. The total within cluster sums of squares is 1,149. So then the question becomes, this is turned into like a big review for this question with how to run the algorithm and stuff, which is kind of the important part of this question. The question has then become, back to our elbow plot right here, you know, we want the y variable to be the within cluster sums of squares, which we got right here. And then we went over the vector of 1 through 10. And if we do the tilde, it will do it. Plot will take this. It's going to say figure's too large. Whoa, whoa, whoa. What just happened here? Make sure it works. What am I doing? That's right. Invalid terms. What are you mad about? No. Is it mad about the... Really? Really? Yeah, I don't want the 1 through 10 there. I just like that it doesn't like that. There we go. Not that amazing. Not that amazing elbow. Awesome. Glad this helped out right here. This elbow plot, not that great of an elbow. Not that great of an elbow. And so we could go with 5 cluster scheme. And here's what we're going to do. We're going to go right here. We're going to look at our 5 cluster scheme on this. So look at our 5 cluster scheme, which is what we're doing in this question, is we're going to go right here. We've got our crazy, crazy data. Let's go to our crazy data. And where's our crazy data? Our crazy data is right here. Our complete cases, scaled new data. And we're going to store into this the values, or we're going to write into it cluster code, cluster 5s. And from this, we're going to take, let's rerun this here so it only goes to 5 now. Okay. We're going to take from this the cluster IDs, which go to 5, and store that as a vector onto here. What's it mad about? Warning, incomplete case, coercion, LH to list. Might have done all right. Let's go find out if it did it all right. Did it take it? It was a warning. Yeah, it's all right. It took a warning, turned it into a list, and it worked. It took it. So we go, put a list. Ooh. That's not good. That's not good at all. Maybe I should have stored my object again. I might have just broke everything. Remove complete cases. There's no undo button. New data. Ooh. Where did that change along the way? Let me watch that. Oh no, it's still a diaphragm, right? Where's the new data? There's the new data. Okay, it hasn't been hurt yet. Oh, is it right here? That's where it got damaged with the S supply. Really? Let's run this again. Should have looked at that. Okay. Now we're doing better. That's fine. Okay, good. I think we've done it. Do I store it? This is where I store it down here. Okay, good. So watch out. I didn't even realize that. I turned it into a list. It output a list. I think Trace mentioned something about that earlier. So I changed the way the object was, but I've got my cluster IDs right now. So what we've done, the whole point of this is to put these cluster IDs to these individuals. So we have cluster IDs for these individuals right here. So you can tell what clusters people are a part of. And we get a better idea of like what kind of we have for each individual. And let's take a look at some of these clusters real quick and see if we can identify some themes between them for the clusters. So we need to go here to the aggregate. We're going to look at the median for each cluster, like their median z-score, because we have standardized this. So we're actually going to pick all the y variables, which is the dot. We're going to use the tilde to use the formula format here. And then we are going to use the cluster ID I created to separate them by. So the aggregate function takes the formula format right here with the way you want to separate things and the way you want to analyze the y variable of interest, y tilde x. We got to do some data equals here. Data equals. And we've got our complex, crazy little thing right there. And then we have to go to fun. I believe it's capital fun. Is it lowercase fun these days? Only one way to find out. Some of these take, let me change my window right here. It's uppercase fun. It's always uppercase fun. And then we go right here and we're fixed. It's always remembering the combinations. Some of them take lowercase fun. Lowercase fun's a function, right? There we go. You just have to know which one to use and when, and sometimes you got to keep it in your head and you forget. Here we are with the cluster IDs, and what do we notice? Okay, so these are all z-scores. Ooh, I don't like the way. We make this look a little bit better. It's so long. Right here, these are our workers. Ooh, don't like these z-scores. Not really any differences across here. Not any differences across here, but we do see the workers. We see the people who want to weigh more. Ooh, here's our gym membership people right here. And these are going to be our gym membership people. They want to weigh more. I'm assuming they want to get stronger. Good job, Kayla. Excellent work. Saying good luck to Trace right there. These people weigh more than average, and they want to weigh more than average. Do you see that right there? That's pretty interesting. And I'm thinking maybe we shouldn't go for 3 clustering schemes. Let me change my code right here and go to 3. So now we're going to just take and store the k-means 3 on here and switch it down to k-means 3. And here's our 3 clustering scheme group. Whoops, stop doing that. I don't like that it's so small. We want to subtract off. I think we can do dot minus. It's got the extra scheme in there, so I don't want the 5 cluster scheme. Let me remove that. Complete cluster. I'm going to remove off the cluster scheme 5 by nulling it out. It's just getting in the way of the output right now. Here we go. And we still see, and I really noticed this right here, you've got your people who, I should have went down to 4 maybe, but I'm just going for a good answer that I like. I really noticed that these people right here in cluster 3 want to weigh more or weigh more, and they want to weigh more. Their desired weight is much heavier. These groups look to be mostly above average in everything. And we are looking at the median right here. Remember, the mean will give us a different look at it. So we could look at this, but this is going to include outliers right here. I would call these people the people who really want to get bigger. And usually, I think, I could be wrong, but I think getting bigger, especially if we're doing gym stuff, probably means, I've always, maybe it's just my guy viewpoint, because usually we understand the world through the ways we've seen it. But whenever someone says, I want to get bigger, I'm thinking, oh, you want to put on muscle. So these people weigh more and they want to weigh more. So I'm thinking they might be prime candidates for hey, you want to put on some muscle, you want to get strong. These people want to lose weight. So maybe we advertise weightlifting to these people, and then we advertise cardio to these people. So these people weigh less and want to weigh less. These people are somewhat satisfied with their weight. They're a little bit above average and want to weigh a little bit more than the average. They also work out a good bit, which is interesting. There are people who they're not that high though. You look at their z-score here. But overall, I think these 3 groups might be my marketing strategy. Once again, there is no real answer to this. And we could bring these back to the real units of the problem. We would need to take and untransform this data. But probably the easiest way to do this is to take, and let me remove out those people. Let me go to survey 10 or survey 9, and this will be the end right here. Really, the answer becomes, let's remove out, we had to remove out, if you remember from early on, these people right here, and we went to complete cases. So let's go here to survey 9, and let's remove out those people. And survey 9, step 1. And then let's go here to this. And step 2, we did complete cases. So we need to go to complete cases, which will only get the rows where people entered in all the values. And now we should get, if we go right here, we've got the same stuff. We can store in the cluster IDs. So I'm going to go to my cluster IDs right here that I have for 3 clusters. And they're the same cluster IDs. If I have the same size, so let's go here to cluster 3. And does it same size? Oh, what? How did we not? Complete cases. How did we get different sizes? We shouldn't have different sizes because we were moved out. I'm going to have to take a look. I got a meeting coming up here soon. I would think we have the same size. Complete cases. And, oh, I know why. Oh, man. The reason being is when we went to complete cases, we did it for the full data frame. So, you know what we need to do? I know why. Theory is tough. So let's take, last second right here. So let's take survey 09, only take those values. Survey 09, complete cases. Survey 09, take from survey 09, complete cases of survey 09. Because there were other rows with missing cases. That's why they didn't match up. Survey 09, complete cases, cluster code, cluster 3. And now we need to take right here this and store into here. And now, summary, let's go. Nope, let's just regrab our code we've already written. And let's take it down to here. And we can see that we have everything we need except for changing the data frame. And we should have the same stuff. And here we are. And this really gives the context of it. And this is a good place to end it. Because if you look at this, you can see that cluster 2 right here is our people who weigh a little bit more and also want to weigh a little bit more. Cluster 3, interesting when you look at this, they weigh at this amount, but they actually want to lose a little bit of weight. Everyone wants to lose weight except for these people. These are the people who want to maintain. They're actually very happy with their weight. And I think that gives a little more context here to look at the actual values, to look at the untransformed values, because we saw they were closer to average. So these people are kind of, they're happy with their weight, their maintain weight. Maybe we send them something like maintain your weight. And then these people right here, everyone wants to lose weight. These people really want to lose weight. I was wrong about kind of thinking about that they want to gain muscle, but they might be better candidates for putting on muscle if they have a little bit of weight. These people also, they don't want to put on muscle though. These people generally right here are the people who weigh less and want to weigh even less. It's just the theme of everybody, right? They're also working a lot. So maybe we could advertise they work a little bit more than the other people. We could advertise a after you work, get off right here. These people also are going to the gym way more, which is interesting. Kind of an interesting thing right there. It seems like they're pretty happy with where they're at because, I mean, that's a 0.1 difference. So very interesting how that lines up right there. They also like to drink. So maybe we throw social events with them. Maybe we throw like, hey, social event at the, thing at the gym. Like, come to the gym, work out, and social events. We want to keep them happy, keep them customers. Well, that's got it. I'm going to head off. I've got a meeting. Great job. I hope this helps better understand the k-means algorithm right here and how we're using clustering to create these clusters and create some sort of idea on how to market these people. We'll be back here for 201 in just a little bit. Till then, where's my music? Here we go. Bye for now, everyone. Bye.